We generally use many construction materials to execute fabrication, build and manufacture different members or parts of structures. Such members need to be analyzed from engineering point of view. We should learn and know their different engineering properties. Some of members exhibit nice performance in one engineering property but may perform poor in other. The material which is good in their selected engineering property are used in that specific purpose. Like copper is very ductile and nice conductor, so it is used in manufacturing wires and cables. Steel is good in taking tensile stresses, so it is used in reinforcing bars. Concrete is good in compression, so it is used in columns and other compressive members. Next we learn different engineering properties of materials. Elasticity. Property by which material regains its original shape after removal of external load. Example is rubber. Plasticity. Property vice versa to elasticity. If a material fails to regain its original shape after removal of external load, then it is said to be a plastic material. Example is plastic. Ductility. Property by which material can be drawn into thin wires. Example is copper. Brittleness. Property vice versa to ductility. Glass is brittle material. Hardness. Property by which material can resist indentation or scratch. Example is diamond. Toughness. Property by which material can bear sudden load or impact. Example is galvanized iron sheets used in roofs. Malleability. Property by which material is given various shapes with mallet when hot. Example is mild steel. Tension forces and tensile stresses. When a member of length L is subjected to pull at both ends, its length increases. Then stresses developed in member are said to be tensile stresses. And pull may also called as tension force or tension. Let it has uniform cross-sectional area equals A. Change in length equals dl. Then tensile stresses in member is sigma equals P upon A. Also change in length is calculated by dl equals P into L by A into E. Compression forces and compressive stresses. When a member of length L is subjected to push at both ends, its length decreases. Then stresses developed in member are said to be compressive stresses. And push may also called as compressive force or compression. Let it has uniform cross-sectional area equals A. Change in length equals dl. Then compressive stresses in member is sigma equals P upon A. Also change in length is calculated by dl equals spin TL upon A into E. Let us discuss very important terms, known as stress and strain. First, understand stress. It is defined as resistance to external load per unit area. When a bar of given material changes its length under action of external load, every molecule of its cross-section sets a resistance against deformations, to maintain its intermolecular distances. Such resistance, if calculated over unit area, is known as stress. Units of stress are megapascal or Newton per mm square, where 1 pascal equals 1 Newton per square meter. Next important term, which is mostly used in calculations, is known as strain. The ratio of change in length to original length is known as strain. It is a unitless parameter. It is denoted by epsilon. Epsilon equals delta L by L. Stress-strain curve of mild steel. To know behavior of different grades of steels under loading, we need to perform tension tests over them. When a mild steel specimen bar is used in universal testing machine, its length between jaws is marked at 2 points, over which the extensions are read at different rates of loadings. Thereafter we can calculate stresses and strains at various salient locations up to local failure at critical section. The marked length over mild steel specimen, for which stress and strain relationship is gathered from tension test, is known as gauge length. When a mild steel circular or square bar undergoes tension in universal testing machine, the stress and strain follows the above curve up to failure. The salient features of above curve are: OA range, stress is proportional to strain and is called as proportional range. The material undergoes deformations in elastic range. If load is removed, the material regains its original shape. Hooke's law is valid in this range. Stress is proportional to strain. That is, sigma is proportional to epsilon. Sigma equals epsilon into A, where A equals Young's modulus of elasticity in Newton per square millimeter. P upon A equals delta L by L into A. Delta L equals P into L upon A into A. Change in length is calculated from above formula. OB range. Elastic limit, up to which material regains its original shape. AB range. Non-proportional range, now strain accelerate more with respect to stress. BCD range. Yielding zone, strain increases without further increase in stress. From point B onwards, plastic deformations start. BA range. Second non-proportional range. A is point of waist or neck formation over critical section of the specimen. The stress corresponding to point A is called the ultimate tensile stress of the material. AF range. Material ahead in local failure zone. As the extension is increased, the load required decreases, the specimen breaks at point F. The stress corresponding to point F are called failure stress.
For complete course and step-by-step illustration, please subscribe full course on Structural Analysis and Design app. Also subscribe YouTube channel Maatrixx Digital Solutions. Thanks for watching.